Here we go. Recording. Good stuff. So, we're going to take a quick sort of diversion into Chapter 3. Because there's certain things that I like to be able to do with derivatives, certain points of view I like to be able to take on derivatives while we're in Chapter 2 that the book doesn't get around to developing until Chapter 3. So quick little jaunt, and here we go. We're going to talk about derivatives of parametric curves. So y'all remember parametric curves, right? This is where you have a vector valued, right, function, but it's giving position, and position as a function of just the one variable usually thought of as time, right? So position as a function of time. We wrote down formulas that look kind of like this. Cool. So let's ask the question, what does the derivative matrix look like in that case? Well, if there's only one input variable, and remember, the structure of a derivative matrix is that, among other things, columns correspond to input variables. If there is only one input variable, then your matrix has only one column, right? And so there it is. It's just the derivatives of all of the position coordinates, all derivatives with respect to time. And you may be thinking, wait a minute, aren't these supposed to be partial derivatives? But there's only one input variable, so they're not even partial derivatives. There are no other variables to hold constant. They're just regular derivatives. And then if you look at this formula here, right, this expression right here, that's just one at a time, one coordinate at a time, the derivative of the position itself. So this is literally dx dt. Of course, this being the usual single variable derivative defined by this formula. Right? And if you're maybe a little curious, wait a minute, are we sure that we can apply this formula one coordinate at a time as would be necessary to sort of, if you will, distribute that derivative to the coordinates? Well, I'll point out that if you just look at the expression for this single variable derivative, right, and ask, how do I compute the various participants in this story? They're all done coordinate-wise. How do I subtract two vectors, one coordinate at a time? Right? How do I take a vector and multiply, in this case divide, but by a scalar? Well, one coordinate at a time, right? Again, we kind of skipped over the business about limits, but I'm going to just assert here limits. You can deal with one coordinate at a time as well. So, yeah, so it all works. So the derivative matrix is, in this case, just the calc 1 time derivative of position. So let's make an interpretation of that geometrically. And y'all may think to yourselves, we already have a geometric interpretation of this, right? Wouldn't that calc 1, isn't that supposed to be like the slope of the tangent line or something? Okay, here's the very important point you always have to realize. That's if you're looking at a graph, right? And so this issue comes up a lot of, you got to make the right geometric interpretation in the right context. Right? And in this case, we are not typically, if you're looking at a parametric curve, you are typically not looking at a graph of your parametric curve. You're usually looking just in the target, and you're looking at the image curve. As time passes, you're looking at just the outputs. Right? So this is not a graph, and so this thing here is not going to be anything about slopes. So make sure to keep that distinction clear in your mind. This is not going to be interpreted as a slope because we're not looking at a graph. Okay, enough about that. So let's get to it then. How do I make sense out of this? Well, I've got some point x of t. And now I want to look h seconds later along that curve. I'm at some other point like that. And you can look at this difference vector. That difference is what I have in purple here. Now, don't forget we're supposed to divide by h, right? You divide by h, and now notice I've got the x of t plus a. I got that second point substantially down the curve, right? So I'm trying to draw an example here where h is a larger than 1. This is not supposed to be a micro h. So when you divide by h, you're going to get a vector that's a little smaller in this case. Right? And now we can ask the question, well, what happens if we take a limit as h approaches 0? Well, in that limit, a lot of things are going to happen in the limit. And I'm going to clean up my picture for a second. In the limit, as h approaches 0, this point here is going to get closer and closer to down here. And so the displacement vectors are going to be getting shorter and shorter. Yeah, absolutely. Right? But then we're also going to be dividing by smaller and smaller numbers correspondingly. Right? And so in terms of magnitudes, you'd kind of expect those kind of roughly, in some sense, to cancel out. But what about in terms of direction? Notice that the direction that this overall vector points, right, that direction is always, it's parallel to that secant line defined by the 2 points in question. So the only thing that we expect to really be changing significantly is the direction that it's pointing. And as I get closer and closer, as I get closer and closer on the curve, anyway, you get the idea here. As you get closer and closer on the curve, these secant lines are going to become closer and closer to being tangent lines. So now that is one thing that this does have in common with the Calc 1 interpretation, in the Calc 1 context, is that there are secant lines that in the limit become tangent lines. Same here. It's just that we're not looking at slopes of these things. We're looking at vectors pointing along these things. Right? So big distinction. Nice punchline. This eventual result here, let me go back to highlighter mode. This eventual result here, this thing that is x prime, it points in the tangent direction. It points in the direction that the curve is going. And let's think momentarily now about what is the speed that we're moving in here. What is this? I got ahead of myself. What is this? What is the magnitude here? And notice that the magnitude of that is displacement, and we're dividing it by an elapsed time, and distance divided by time is speed. Okay, got ahead of myself. Okay, so all together then, we have here a vector that points in the direction that we're going and whose magnitude is the speed. And this is an old concept. This is the concept of velocity, physical concept of velocity. Okay, so you may recall I kind of used this interpretation already once, and this is why it works, right? And we're going to be using this concept actually quite a bit going forward. So, so the derivative of a parametric curve is the velocity. Pausing for questions. Is everybody happy? Okay, so and then similarly, the derivative of the velocity, namely the second derivative of position, is what we call acceleration, and another standard physical concept. Okay, so let's see some examples. Let's suppose that we have a velocity given as a function of time, and suppose we also know some starting position. Right, now y'all may remember this kind of category of question from single variable calculus classes. Given the velocity, kind of you want to work backwards, kind of reverse engineer what the position is, and you have to be given a starting point because, of course, velocity tells you nothing about where you are. Okay, so all right, so I'm going to start off with the easier question, which is given the velocity, what is your acceleration? And of course, acceleration is the derivative of velocity per the previous page. And derivatives are computed one coordinate at a time, and so this is an easy derivative to compute. So acceleration is sort of the easy part. It's just a matter of taking a derivative. Now, where it gets a little bit tricky is, again, reverse engineering the velocity to figure out what the position is. So what is the position? Well, position is the antiderivative of velocity. Let me be more careful about that. It's an antiderivative of velocity. right? And there's actually a bunch of antiderivatives. We'll have to deal with that ambiguity later. But first, let's compute an antiderivative. And how do I compute an antiderivative of a vector-valued function? Well, just like with derivatives, one coordinate at a time. Right? So one coordinate at a time, this vector-valued antiderivative, it's just a vector of a bunch of antiderivatives. And these are single variable antiderivatives, and so this is a single variable calculus. And by the way, this is a good opportunity to remind you all that integration stuff from Calc 2 is all going to, well, most of it anyway, is going to be it's going to come up here and there. It's going to be assumed, certainly, in this course. So make sure that you're really good with all of your integration tricks, anti-differentiation tricks. So integration by parts, substitutions are really the two huge ones. But don't forget, there's a bazillion little formulas for like trig functions and stuff. And then there's a few clever tricks of how to use substitutions and integration by parts for things like trig integrals, like if you have sine squared times cosine cubed, how would you take an integral of that? Right? This is the little tricks that you just have to make sure to remember what the trick is. Don't forget your half angle formula tricks, right? Those are very handy, right? So there's a lot of stuff in there. Make sure you're good with all of that. You don't need to worry about like I'm gonna say relatively obscure stuff like hyperbolic trig functions, which have their uses, but we're not gonna, it's relatively obscure. It's just not gonna come up in Math 219. Okay. All right. So make sure you're good with all this stuff. And now, one thing else to remember: when you take an antiderivative, don't forget you have to add a constant. Right? After all, the job of our answer here is it needs to be something that when we take its derivative, I need to get velocity back. And when you take that derivative, in the action of taking that derivative, whatever constant you put there is going to disappear anyway. So it's fine, right? You can't rule out that there might be a constant there. Said differently, the antiderivative that you picked, this one that you wrote down, is pretty arbitrarily chosen, and you just can't assume that your arbitrary antiderivative is the correct antiderivative. Okay, so now to evaluate this constant, what is this constant? The big trick there is take whatever time you have information about position, and of course that time is 0, right? We know what happens when t equals 0. Take that value of t and plug it in and see what happens. And if you plug in t equals 0, well, position becomes 5, 6. And you plug in t equals 0 into this formula right here, and this expression here becomes 3, 1. Right, just plug it in. And of course, C is still C. This just is sort of waiting for something to happen. Nothing really happens there. That's the unknown we're trying to solve for. Yes?
So if 5, 6 is position, are we plugging in acceleration?
I'm sorry, say it one more time.
So if 5, 6 is like the position, why do we plug in acceleration?
Not plugging in acceleration. No, acceleration is up here. Yeah. This is we're done with that. That was just kind of a part A. Yeah, that's right. So we're good. Yeah, right. Okay, yeah. So plugging in for the position and plugging into the formula, and well, we have a little equation here then that tells us what our statement about position says at time equals 0. Well, at time equals 0, it's really easy to solve for C then. You just kind of subtract, and there you go. There's your C. So this C goes there, and that completes our formula for position. Position is all of that together. Is everybody all right? All right, now I do want to warn you about one big thing and then one small thing. The big thing is there are a lot of students who seem to be under a misconception that this constant is always equal to the initial value. And the reason a lot of students think this is because in their single variable calculus classes, it always worked out that way, every single time. And the reason it always worked out that way every single time is because every example they saw in their high school calculus class, this thing here ended up being 0. The reason that always ended up being 0 is because there was a common factor of t in every term in this expression. And the reason there was a common factor of t is because the velocities that they were given were exclusively polynomials. Now, so it's just a little bit of what I'm going to call laziness on the part of the textbook, right? High school calculus textbooks, and this is not rare, and they'll just say, well, look, we don't need weirdo functions like trig functions and exponentials, let's just stick to polynomials, we'll keep the derivatives as easy as possible. And so they always use polynomials, which means they will always have a common factor of t in every term here, which means they will always get 0 there, which means it will create this illusion that the constant of integration is always the initial value, and it's just an illusion, right? Based on that one sort of lazy choice. So anyway, please don't fall for that trap. You see here, easy counterexample, this c and this initial value, absolutely not constant. Of course they're not. Look, there's a big 3, 1 right there. They're totally different. Right? So heads up on that. Very common mistake to make. Okay. Then I'll point out just, a real quick observation. This integral that we do here, well, first of all, it's an antiderivative, not an integral. That's one of my little pet peeve soapbox topics. Antiderivatives and integrals aren't the same thing. If you're not entirely clear what I'm talking about, come talk to me in office hours. I'll be happy to elaborate. They are different. Or if you don't want to come to office hours or can't or what have you, I have a video on this topic on my YouTube channel, Miscellaneous Topics playlist. It's called What is an Integral? And I get a lot of stuff off my chest in that video of common high school misunderstandings of what integrals are and what you can do with them and what notations and stuff like that. Okay. So point being, a lot of students will look at something like this and think, oh, it's an integral, and integrals are area under a curve. And I just want to point out, this is just not at all what's happening here, right? Again, integrals are not antiderivatives, and furthermore, integrals give you area under a curve only if you're looking at a graph of that function, right? Which we are not here. And so that's another calculus of graphs that you don't want to inadvertently import into a totally different geometric concept. So it's just not area under a curve. Okay, how are we doing? Pausing. Okay, so there's a bunch of other stuff in this section of the book that you're not responsible for. Reminder, keep an eye on the content syllabus, because there's not only excluded material listed there, the things that you don't need to know, right? So we're not going to cover any of the Kepler stuff in this section, right? But there's also, just as a reminder while we're on the topic, there's also lists of included material, stuff that I will talk about in class even though it's not in the book, that is part of the course and that all students are responsible for. In this case, anyway, I'm pointing to the stuff that you're not. This is listed on the content syllabus as excluded material, so don't waste any time. If you're curious, if you want to, you're very welcome, and it's, good stuff, I suppose, but it's not part of the course. That said, there are a couple of things that do need to be noted, and roughly speaking, these are just sort of product rules for parametric curve derivatives. And they're exactly what you would expect, but then again, there is a lot of statements that one can write down that one would expect that are also not true, right? So the fact that these are true is worth noting. Okay. All right. That's all we're going to do with 3.1. Moving on now to 2.5. Well, moving back, right, to 2.5. So we had finished 2.4 last time. We jumped up to chapter 3 for a real quick discussion, and that's going to make it easier for me to talk about the chain rule, which we're going to start on now, 2.5. Okay, so single variable calculus. Y'all remember single variable calculus, and my point here is not that you don't know this. My point here is that I want to establish a specific point of view on derivatives that is particularly helpful and that we're going to use quite a bit in this section specifically. And yes, there are other points of view on derivatives. Yeah. This is the one that was going to be useful in what we're doing right now. Okay, so specifically, the derivative is the thing that you multiply by an input velocity to get an output velocity. Right? So it's a relationship between input changes and output changes. But specifically, not as a ratio. Don't think of this as a ratio. Think of this as a factor. And I know they're kind of the same thing, right? But nevertheless, importantly, I want to think of this as a factor, not a fraction. It's a thing you multiply by 1 to get the other. Okay. Alrighty. So now I'm going to consider now a composition. We're going to look at a couple of functions. Here's f. F is a function that takes in x and spits out y. And now we're going to consider this other function called g. G takes in y and spits out z. And when you have two functions like this, where the output from one then is the input for the next, then you can talk about the composition. And this composition takes in x and spits out z. Right, that's our standard story for composing single variable functions. And now I'm going to write down some observations. I got 3 functions here. These are just single variable functions. And this point of view of observing a derivative as being a factor is perfectly fine and applied to all 3 of these functions. So here we go. Starting with f. Here's my function f. Here's the derivative of f, interpreted on this context that if you have an input velocity and there's a corresponding output velocity, then the derivative of f is the thing that you multiply by the input velocity to get the output velocity. Alright, nothing happened. That's the exact same thing we did before. Now, let me now apply that over here to this function, g. Well, we have an input velocity, now y prime. We have an output velocity that results, namely z prime, and the derivative of g is the thing that we multiply by the input velocity to get the output velocity. So, same statement, just applied to a different function with different variable names. Same concept. Everybody happy? And one more time, we'll do it for the composition. Don't forget the composition is a function that goes from the x variable to the z variable, right? That's what this composition does. And there is an input velocity x prime. There is an output velocity z prime. And those, again, are related by the derivative. Oh, I'm sorry. I circled the wrong one. Okay. Input velocity x prime, output velocity z prime, related by the derivative of that composition, in this case dz dx. Okay, so that all I've done here is I've made the same statement 3 times, just in application to 3 different functions. Yeah.
In this case, the prime is not referring to a derivative, is it?
Yeah, a time derivative. So imagine everything here is moving, and so derivative with respect to time. So in fact, if you really wanted to, we could think that there is in fact another axis over here. There is a t-axis over here, and x is a function of time, and then etc. As a result, y and z are functions of time. Yeah, totally. Is that cool? Okay. All right, now with all of this noted, here's the little move I'm going to make. This is now just for the sake of the algebra of it. What I'm going to do is I'm going to take this formula for y prime. I'm going to plug it in for that y prime right there. And then let's look and see what this equation 2 turns into. And well, it turns into this, which of course you can rewrite as that. Now, that's just plugging in. I hardly did anything. Right? I got a formula for y prime. I plugged it into that second equation. I get this stuff on the left. And now, that's, whoops. That was this, plugging 1 into 2 gives me this. And now I'm going to compare that with this equation up here, number 3, and comparing. Notice I've got, in each case, something that you multiply by x prime to get z prime. Well, these two things then, this thing that I multiply by x prime to get z prime, and this thing that I multiply by x prime to get z prime, must be equal. And that's my chain rule. Single variable chain rule. That's just one way to think about it. Now, the streamlined, non-algebraic way to think about this is really a lot easier, and that is that, if I think of derivatives as being factors, then in the process of going from sort of x world to y world, velocities get multiplied by a factor, and then after that, in the process of moving from y world into z world, I multiply by another factor. And if you think about it, if you have something and you multiply by a factor and then you multiply by a second factor, altogether you've multiplied by the product of those two factors. Right? I mean, factors multiply, I guess is you'd say. It's really not a deep point if you think about it in that sense. If you have something and you multiply by 2 and then you multiply by 3, altogether you've multiplied by 6. That's all. Right? Not that big a deal. Okay. All right, so that's the single variable point of view. Now I am going to point out that what this is saying then is that differentiation turns a composition. Keep in mind I had a composition of functions here, but when you take derivatives, that composition then turns into a product that you can see right there. So this is kind of a, rolls off the tongue point of view, a way of remembering the chain rule. Differentiation turns a composition into a product. Okay, now with all this single variable stuff, refreshed in our minds, I hope, let's take an analogous point of view for multivariable functions. We're going to try to come up with a multivariable version of this same thing. So, all right, starting with, what is a derivative? Well, if we have an input velocity and an output velocity that results, right? Remember, one of our big interpretations of the derivative is that the derivative is what you multiply by input velocity to get output velocity. So it's a factor. Just like in the single variable version. Here, the derivative, you can choose to think of this as a factor. So I'm going to take this exact same point of view in the multivariable context that we already knew. Derivatives are factors. Okay. All right, and with that in mind, here is a composition of functions. And so here's, f turns x's into y's. Yeah, there's 2 different x coordinates. There's 2 different y coordinates, but nevertheless, f turns x's into y's. G turns y's into z's. And their composition turns x's into z's. So, same kind of a setup that we had on the previous page. And now again, we can write down what the derivative means in all of these situations. In this context here, we're looking at the process of f turning x's into y's. Well, then the derivative of f relates x prime and y prime. For this second function that turns y's into z's, the derivative is the thing that turns the y velocity into the z velocity. Same point of view. Right? And then lastly, looking at the composition that turns x's into z's, well, the derivative of that then is what multiplies by the x velocity to give you the z velocity. So same idea as before. We're going to use this factor point of view on the derivative. and just apply it to a composition in the obvious sort of three different ways, just like we did in the single variable case. In fact, let me scroll back here. Same setup. 3 functions, 3 interpretations of derivatives. And I even went to some trouble to lay it out on the page the same way to help see the analogy. Right? Okay. So guess what? We're going to do the exact same thing we did before. We're going to take this formula for y prime. We're going to plug it in there. And the result, I guess I do need to come back out. Plugging this into there turns this equation into that equation. Now it's a little uglier looking because these derivatives, the notation's a little clunkier now, but still it's just, that derivative gets multiplied by the thing that was what something else got multiplied by a different derivative. It's just plugging in, right? Which gives me this. And I can then compare that with this equation, and the same kind of thing happens. In both cases, I'm looking at how z prime is something that you get when you multiply by x prime, and so these two things that we multiply by must be the same. That and that must be the same things. So we have now a matrix algebra formula for what we call the multivariable chain rule. And let's take a careful look at this now. What this says is that if you have a composition of 2 functions, composition of 2 multivariable functions, the derivative matrix of that composition is the derivative matrix of the second function times the derivative matrix of the first function. And this is a matrix multiplication right there. So notice that again, just like in the single variable case, differentiation turns a composition into a product. Just like in the single variable case. It's just that now this product is it's a matrix product, because the derivatives, after all, are matrices. How are we doing? Is everybody with me? Does everybody see how it's the same exact thing that we did in the single variable case? Just, more complicated with vectors and matrices, but it's the same structure of argument. Okay. Good. All righty. Now, we do have to be careful about one thing here, and this is just kind of annoying that we have to be careful with this, but it's an annoying reality, so we do have to be careful with it. Don't forget that derivative matrices have to be evaluated where they're being applied, right? So if I say that df is what relates this x velocity to that y velocity, well, this is a statement I'm making about what happens when I'm at this point A in the domain, right? That point A is where I am when I start moving with velocity x prime, and then the resulting image moves with velocity y prime. So it's at this point A that I've got to evaluate df. So this function f df evaluated at that point where it's being applied. Is that cool? I hope that looks reasonable, right? Okay, cool. Well, don't forget, f is being applied at that point, and of course also the composition also being applied at likewise that same point, still A, right? F is being applied at A, the composition is being applied at A, but G, not so, right? G is being applied at this point, which is very much not A. It's not even in the same world that A lives in. It's just not there. It's missed again. It's in the Y space. So that derivative, the derivative of G, has to be evaluated, well, again, at the point where it's being applied, at the point where I am when I start moving with velocity y prime. which is the velocity that I'm to which I'm going to apply this DG matrix. Right? So real easy to forget that. Y'all will probably remember a single variable version of this if you write down the single variable chain rule in Newton's notation instead of Leibniz. I see back here I wrote it in Leibniz notation, so this all kind of gets concealed in the notation. But in Newton notation, you probably remember the analogous thing. And so don't forget this is at f of a, right there. How are we doing on that point? Is everybody happy? All right. Okay. So, and then a real quick observation. I drew this picture for functions that go from R2 to R2 to R2, right? And what changes when these become like three-dimensional? Absolutely nothing. And I'll just show you as a for example. Here we go. Now this is. Now we're in 3 dimensions here, right? See, I got 3 axes, 1, 2, and 3, right? And this space is now 3-dimensional, and nothing changes in the argument. The output velocities are still matrices times input velocities, and yeah, the matrices change shape, but the argument exactly the same. So even though I only drew the pictures for 2 dimensions, works for all dimensions. Okay, let's see an example. Okay, so we have a function f that takes x's to y's, let's say. And then I have a function g that takes y's to z's. Now you'll notice I am deliberately using the same sort of alphabetic choice of variables as I did on the previous page, right? X's to y's, y's to z's. First function f, second function g. That's just, first time through. We want to keep everything familiar. But of course, let's recognize in the real world, probably not, right? I mean, usually there's some other choice of variables or different names for the function. So don't base your understanding of this on particular letters of the alphabet playing particular roles. Okay, that said, information that I'm given, data that I'm given there. Right, we'll come back and figure out when I'm going to use that as it comes up, as I need it. And here's my question, though. I want to compute the derivative matrix of the composition. So the very first thing I'm going to write down is the chain rule. And if you want to know the derivative matrix of the composition, it is the product of the individual derivative matrices. Okay, now the thing is, I need, so it seems then, I need the DG matrix, but it's got to be evaluated at f of 1, 2. The DG matrix that I have is evaluated at 3, 1, 0. You can't just use any old derivative matrix of G that you want. It's got to be evaluated at the right point because it's got to apply at the right point. So, I needed at f of 1, 2. I have it at 3, 1, 0. Good thing those are the same. Everybody with me? All right, so you got to be careful about that and don't plug in the wrong matrix by accident, or plug in the wrong value or whatever. So anyway, this is what goes there then. And of course, the df of 1, 2 is given also, and we've just turned a chain rule problem into a matrix algebra problem, and now it's just a matter of cranking out a little bit of arithmetic. And boom. What do you think? Everybody's good? I want to recognize one other thing, by the way, and I kind of did this on purpose. You have to be really careful about the order that you write things down. And of course, this shows up in stories like this where, let's see, I'll rewind. Here we go. So here, you see how the DF matrix is on the right, whereas the function f is on the left. And likewise, the DG matrix is on the left, even though the G function is on the right. This is a ever-present frustration with notation. It's a consequence of how algebra gets written down. And had different conventions been made hundreds of years ago, then we wouldn't have this problem. But they weren't, and we do. So all I can say is heads up. Always think to yourself, it's not a question of left versus right. It's a question of what acts first. Right? So F here acts first. Because when you're drawing a diagram, it goes left to right, so the one on the left acts first. When you're multiplying matrices, whatever you're multiplying by over here, right? The thing that acts first is the one that's on the right, because it's the closest to the thing that you're applying it to. So, again, I'm sorry. It's very frustrating, but heads up. And make sure not to accidentally get your matrices backwards. And I'm making a big deal out of this because when I was in grad school, I had I had this thing happen to me. This was very painful at the time, but I had not matrices and such, but there was a problem that I was working on, and when you're in grad school, a long, difficult problem is not one that takes you an hour and a half. A long, difficult problem is a problem that takes you a year and a half. Right, so it was a very huge, intricate, detailed, involved problem, and I'd been working on it for a while. And at one point, there was a situation analogous to this, and again, it wasn't matrices, but it had this analogous kind of backwardness of notation. And I got it wrong at one point, and I didn't discover the mistake for a month. And I had to take a month's worth of work and just drop it in the trash can. So, I've learned through the school of hard knocks, right? I've been stung. I will never make this mistake again as long as I live, I'm pretty sure. Right? I hope y'all can learn from my painful experience and not have to have your own similarly painful experience. Okay. Alrighty. So back to this question. So we just computed the derivative matrix. Great. Notice, though, there is a second part to the question. Second part to the question says compute this specific partial. Here, let me choose a different color. Partial of Z3 with respect to X1. Notice that in the composition gives the Z variables as functions of the X variables. And so a reasonable question, in that composition, what is the partial of Z3 with respect to X1? So, okay, alright, so this thing that we want to compute, partial of Z3 with respect to X1, notice that we're taking the partial with respect to X1. Notice that X1 is the first of our input variables. So, this partial that I'm looking for is, as a result, going to be in the first column of my matrix, and so it's going to be one of those numbers right there. Similarly, notice that, I guess I'll use green, we're looking for the partial of Z3. Notice Z3 is the third of our three output variables. Third output variable means we're going to be looking in the third row. And so altogether then, this element that we're looking for, partial of Z3 with respect to X1, is that entry in the first column, third row, and so the answer is 3. Is that cool? Everybody's happy? All right. Good deal. All right. Okay, a couple of special cases. These are just observations. There's nothing really particularly deep about to happen, so I'm going to go quickly through this. But let's just consider the special case of what happens when composition, right? Composition of two functions. Well, what happens if the initial space over here is just one-dimensional? In other words, what if I have just one input variable? Well, if you have only one input variable, then that first function, its derivative matrix, has only one column. And of course, the composition is also here, I should do it like this. So the derivative matrix of that function has just the one column. And then, of course, the composition also a function of one variable. So its derivative matrix has just the one column. And so this is what the chain rule turns into. Fine. Notice, though, you can take a point of view on this. And the point of view we could take is that you can think of this as the function at hand. F from Rn to Rm is the function at hand, and its derivative matrix relates the velocity of this parametric curve, that input velocity you might call it, with the velocity of the composition parametric curve, that output velocity you might call it. So this, I'm going to say, recovers something we already knew, that derivative matrices multiply by input velocities to give output velocities. So it's not. So this is not a new result, but it's just kind of neat that this. There's a different point of view on that statement about what derivative matrices do. All right. So here's an example of where you can use that. So suppose we have a function like this. Now notice there's 2 input variables. There's 3 output coordinates. Right, and if I have some velocity therefore in my domain, right, input velocity. If I'm in that domain and moving with some velocity, I can ask reasonably, what is the output velocity? What is the overall rate of change of this output vector? And I'm looking for therefore a relationship between input vectors and output vectors. And so the derivative matrix is exactly the tool that will answer this question. So I'm going to multiply my input velocity, which I'm given, 4, 3, by the derivative matrix. I'm going to take the derivative matrix of this function f and corresponding partial derivatives. Don't forget to plug in the point in question. Oh, wait a second. Where is that point in question? What is my point A? How do I know what to put in there? Well, that needs to be given, and it is. We're given that we're at the point 2, 1. So this point 2, 1 has to go into there, and that leaves us with then the derivative matrix being these values at the given point that I'm actually interested in. Is everybody with me? Everybody see that? Okay. There you go. This is your derivative matrix that you multiply by, and again, we've got it down to arithmetic, and there's our output velocity. Okay. Like I say, old news. We in some sense already knew that derivative matrices would do this. Okay, second special case. It's a special case of the previous special case, where not only do we have just a single input variable, and therefore I can think of these as sort of, a curve moving through the x space, and it's, when you plug into f, you get a curve moving through the y space. Now I'm going to further suppose that the output is real valued. Well, that really only changes one significant thing, and that is if there's only one output value, and keep in mind the derivative matrix for this function is what goes here. Well, if there's only one output value, then there's only one row in that matrix. So it's just the observation. This is what it ends up looking like. And we've already kind of seen this point, that when you have a matrix of a single row and it's being multiplied by a vector of a single column, it's effectively a dot product. And so now I'm going to be a little sloppy here, and I'm going to equate that single row derivative matrix with the gradient vector for that function. And likewise, now of course I've got my dx, dt, vector is the velocity. So a little bit of an abuse. Technically the one on top is matrix times vector. The one on the bottom is vector dot vector. But it's all the same numbers and it's all the same arithmetic. So, it doesn't really matter. So this is your alternative point of view. If you have real valued input and real valued eventual output, then you can think of the chain rule as, again, kind of recovering the point of view that dot product with the gradient relates input changes to output changes. Okay, so again, example. So we've got a bird flying around, then momentarily at a certain point moving with a certain velocity. So we have position as a function of time. Position in space. Position in space as a function of time. And then I also have this temperature function telling me a real valued number, temperature, as a function of position. So I have that. Right? And all together, notice I've got real value in, real value out with a composition. And so here I can write down the chain rule again as a statement about dot products with the gradient. And so you take the partials, evaluate at the point in question, and you've got your gradient vector and then dot product. So morally equivalent. Yeah. And we're out of time, so this is a good stopping point. We'll pick up here on Wednesday. Hope everybody enjoyed the game this weekend. Pretty awesome. Yes?
When find the other exam?
It's too soon to say. It depends on what I finish by Wednesday. Yeah. So so just to come to here's the lecture schedule and the fair. My bad. No, it depends on what we finish today. But it depends on what I finish in all of my sections today. So TBD. Yep. All right. See y'all later.